Welcome to this episode of the SCIEX Now Learning Hub, Best Practices in LC-MS series. In this episode, we'll discuss the matrix effect and why it can negatively influence quantitation by mass spectrometry. The perfect accuracy of a quantitation method is its ability to measure the true value for the amount of the target molecule in your sample. In reality, there can be discrepancies between the true and the measured value due to the loss of your target compound by the matrix effect during your sample preparation procedure or by its absorption on surfaces. All of the aspects can negatively impair your limit of detection, limit of quantitation, and the linear range. In this episode, we'll examine the matrix effect in more detail. The matrix is anything that is in your sample which is not your target compound. So the matrix can consist of salts, solvents, or any other molecule in your sample. They can originate from the sample itself or be impurities introduced by reagents or surfaces. The source of those impurities can be the sample preparation, the LC-MS system, or the labware used. What does the formation of salt adducts mean for your analysis? Your target molecule is detected either as a positively or negatively charged molecular ion. The formation of salt adducts can prevent your target compound from being detected because they may neutralize it, as illustrated in this example of succinic acid. For the same reason, you need to consider if you are really using trifluoroacetic acid, or rather formic acid as LC modifier. TFA typically gives better chromatographic resolution, but it significantly reduces sensitivity because the TFA anion sticks to the target molecule more strongly compared to formate. The formation of salt adducts can also reduce the signal intensity of the target compound, as depicted in this example. In the positive ion mode, molecules can either be ionized by the attachment of a proton or cation, here for instance a sodium ion. The signal will be split in two. In this example, the sodium adduct reduces the signal of your precursor by 30%. It is not uncommon that the signal intensity of the salt adduct remains at the same level, so higher amounts of your target compound will not be affected in the same way as low amounts. In this example, the loss for the high amount sample will only be 5%. Hence, salt adduct formation can greatly impact the linearity of your calibration curve. Splitting your signal can also severely affect your lower limit of detection and quantitation. So you need to remove or avoid potential salt sources. You might consider a desalting step in your sample preparation procedure to remove the salt contained in your sample, but you also need to avoid introducing salt yourself. Therefore, you should use clean labware, including the storage vessels for your LC solvents. If they are made of ordinary glass, sodium bleeding can occur, which means that gradually increasing amounts of sodium salt can leak into your LC solvents. Also, you should use LC-MS grade solvents and modifiers for your chromatography. Ensure that you are working with a clean ion source and that your LC system is purged with salt-free solvents. When working with reversed phase chromatography, you can try to remove salt on lime by keeping your initial aqueous gradient conditions for a minute or two before increasing the organic solvent content. In this period, it is recommended to direct the flow into the waste. Another aspect of the matrix effect is the ion signal suppression. Ultimately, this means that fewer ions are detected than are actually present in the sample. To further understand the circumstances leading to ion signal suppression, let's briefly recap the events which take place during the ion formation process. We focus on electrospray here, but you can apply the conclusions to APCI as well. A closer examination of the Coulomb explosions reveals that those molecular ions preferentially pass into the next generation of smaller droplets, which are located on the surface of the initial droplets. Consequently, a smaller proportion of ions, initially found in the center of the droplets, reach the mass spectrometer. If your matrix contains molecules with higher surface activity, these ions can suppress the signal of your target compound. For instance, if you are targeting a polar compound and your matrix contains a high amount of non-polar molecules, such as lipids, it is likely that you experience ion signal suppression, leading to reduced sensitivity, unless you can effectively separate them by your chromatography or sample preparation. Also, if there are simply too many matrix molecules, it becomes less likely that your target molecule will win the race. In summary, any substance that is not the target molecule in the sample is called matrix. The matrix can negatively affect the detection of your target molecules, a phenomenon known as the matrix effect. This issue is particularly significant when measuring small quantities of the target molecule. The matrix effect can be caused by the formation of salt adducts that neutralize the target molecular ion, or the suppression of ion signals during the ionization process due to a higher surface activity. And it results in an increased limit of detection and quantitation, as well as a reduced linear range compared to pure samples. Thank you for watching this episode. To view the full training course, including progress checks and a final quiz to earn a certificate, go to SCIEX.com. Log in today to take advantage of the highly rated training material offered in the SCIEX Now Learning Hub. You can use the links below.